board on this computer, and I guess it's recording. I see this little dot flashing on and off. I guess that means I'm recording. By the way, if anybody here has a suggestion, sees me make a mistake or has a suggestion as to how to do this or that in LaTeX or manipulating the Apple computer, the iMac that I'm using, and so forth. Let me in fact, I'm going to make this quite a bit bigger so everybody can see more easily. I'm going to move it over there, and I'm going to start at the beginning. So I'm going to try to go over chapter 1 as quickly as I can, well, as quickly as is reasonable, and then try to finish the first 10 chapters before the end of the term so that we can do general relativity and some other things that are of more interest. Now, I realize that it's hard to ask a question when you're confused about what I've just said. Oh Lord, what is that? Photos, quit photos. I realize therefore that it's hard for you to ask questions, but if you want to ask a question, feel free to ask a question and feel free to speak up. I may have inadvertently left everyone. I don't see the controls anymore. That's not a good sign. Here they are. So do I need to do anything to, well, let's get chat going. All right, there's chat. But I want to make sure that you guys can talk. So, and I think what you can do is you can either start your video or unmute yourselves if you want to say something. And so, as I said, it's hard. I realize it's hard for you to ask questions unless you are an expert on the material. And but if you have a question or something's confusing or I skip something, let me know.
Well, it does look like we have full access to our microphones in the chat and everything, so that's all set up.
Great, thank you. I'm going to start at the beginning, and I'm going to have to skip various things. I'd urge you to read all of chapter 1. You know about the natural numbers, which are just the integers, the rationals, or ratios of integers, and the rational ones are the real numbers that aren't. The complex numbers, I'm sure you know about complex numbers, but recall it's z is a real number x plus I times another real number y, and I squared is -1. And so there are some details about complex numbers here. Now, I put Grassmann numbers in the first chapter, which is kind of silly, perhaps, because we're not going to be using them until chapter 20. But I thought I'd just mention them to you. The idea is that they anti-commute with each other. Any two Grassmann numbers anti-commute. And so if you set I equals j, you get 2 theta, you get theta I plus theta I with theta I. It was 2 theta I squared is 0, so theta I squared is 0. So the square of any Grassmann number vanishes. What's amusing about Grassmann numbers, or among them many things that are amusing about them, is that if you have a function of two Grassmann variables, it can only be a quadratic form like this, because any higher structures would involve squares of Grassmann numbers, and they immediately vanish. There are some conventions. I'm going to skip them and just go directly to an important question here. Important concept: an array. An array is an ordered set of numbers, and they play a big role in mathematical physics. Of course, you have an n-tuple, which is a row vector if you write it horizontally, a column vector if you write it vertically, an n vector if it has n components, simply a vector. And the numbers A1 through A2 are called the entries or the components, or sometimes the elements. A two-dimensional array is particularly important in mathematical physics, especially quantum mechanics. It's called a matrix, and the numbers AIK, the entries, elements, or matrix elements. I labels the row, K labels the column. You can add arrays like this. For matrices, you add two matrices, element by element. In this way, you can multiply an array by a number. Z times the whole array is Z times the whole array, Z times each element. You can multiply an n vector by a matrix, and then you get this structure here, which is, of course, very important. And then here are various examples. So I'm going to skip the examples, but I urge you not to skip the examples. So you should read the examples, especially if you haven't had a good course in linear algebra or a quantum mechanics course that emphasized linear algebra. One concept that's often left out of a description of linear algebra is the idea of an outer product. So if you have an n-tuple A and an m-tuple B, the outer product is an n by m matrix. And so that's one way of getting a matrix. If you multiply them in the opposite order, you get an m by n matrix. And you can do all kinds of things with outer products. It's quite varied. Inner products are a little more restricted because the arrays have to be of the same size in one dimension at least. So the inner product of two real n-tuples is just the sum of the products of their elements. But of course, they have to be of the same length. They have to have the same number of elements, otherwise it doesn't make any sense. The Hermitian inner product of two complex n-tuples, well, by convention, we complex conjugate the first of them, and so we get a sum like this. The inner product of a vector with itself is non-negative, both in the case of real vectors and in the case of complex vectors, if you're doing a Hermitian inner product. A matrix times an n-tuple is, well, it just maps the n-tuple into another n-tuple. And or actually let's see, this is mapping an n-tuple B into an m-tuple B prime. So it's more general than n to n. You can multiply two matrices together if their size matches. That is to say, the second dimension of the first matrix matches the first dimension of the second matrix. And basically this in practice works out particularly nicely when all the matrices are square and they're all n by n, so you can multiply them all together. Matrices, of course, are two-dimensional arrays. The trace of a square matrix is the sum of the diagonal elements. I think one can define the trace of a matrix that is not diagonal by, in other words, if here we have a matrix that obviously isn't diagonal, then we just sum along the main diagonal, or if we were over here, we just sum along the main diagonal. I think the word trace is used for that as well, but possibly less commonly, certainly less commonly. The trace of two matrices, it turns out, is independent of the order, and it follows then that the trace is cyclic, because if you do A, B, C to Z, you can move A around and you get that, and then you eventually get C. So that's the statement that the trace is cyclic. I think I should have emphasized cyclic as being a TCM cyclic. Oh, I don't know if it's any point in doing it at this point. I think I'll put this on the class webpage, this version of the first few chapters with some of the important things in color that might help. The transpose of a matrix is, if it's n by L, then the transpose is L by M. And basically what you do is you just take the matrix and you flip it like that. So you take it and you do that. And so you can think of AIK, the sum AIK BIL, that's the matrix product of the transpose of A with B. Transposition inverts the order of multiplication. And now that I think about it, that's something that I should have maybe put in magenta. So that's important, and you can see that explicitly here. If you do the KL matrix element of this, it's the LK matrix element of B transpose A transpose. And a matrix that's equal to its transpose is a symmetric matrix. And the Hermitian adjoint, some people just use the term adjoint. I think mathematicians just use the word adjoint. It's the complex conjugate of the transpose. So A dagger IJ is AJI star. And you can show that the adjoint of AB is adjoint of B times adjoint of A. A matrix that's equal to its adjoint is said to be Hermitian or self-adjoint. So let me see if I can maybe add TCM to that. The Pauli matrices it turns out that these are particularly useful matrices. I know when you first look at them, they look weird, but as you grow older, you'll come to like them better. I don't think you need to memorize them, but you may inevitably. A real Hermitian matrix is symmetric. And if a matrix is Hermitian, then the double sum is real for all complex n-tuples V. And so this is what happens a lot in quantum mechanics. This is, here, let me get this back as being big again. Let me see if I can move this off the screen and make this big enough so that it's obvious even if you happen to have a crummy computer. This happens a lot in quantum mechanics. We take a Hermitian matrix and a real Hermitian matrix. So this is just a real symmetric matrix, actually. And so the average value of any operator in any state is then real. Of course, it's also true that the average value of a Hermitian matrix in any state is also real. The Kronecker delta of course, you know, it's 1 or 0, according to whether I is K or not. The identity matrix, of course, is that. The inverse of any matrix is another, of an n by n matrix is another n by n matrix, such that A inverse A is A inverse, and that's I. So far, we've been writing n-tuples. And matrices with elements as lowercase letters. People often use capital letters. In that case, a matrix whose adjoint is its inverse is said to be unitary. Unitary matrices are square. A real orthogonal, a real unitary matrix is one that's is said to be orthogonal, and it obeys the same rule, but you don't need complex conjugation because the thing is real. And so it's just O transpose O is O transpose is the identity. The orthogonal matrices are also square. And an n by n matrix is non-negative if for all complex vectors, the quadratic form is non-negative. It's positive if the quadratic form is actually greater than 0. So I'm skipping through. Here are some examples of Grassmann numbers represented as matrices. And of course, in quantum field theory, one represents, one gets from a state of n particles to a state of n plus 1 particles by using creation operators. And if they're bosons, then the rule is that the commutator of AI with A dagger is delta IK, and the operators, the A's and the A daggers commute. If they're fermions, then it's the anti-commutator that's delta IK, and the anti-commutators commute. And this rule for K equals I says A dagger squared is 0, and that makes Pauli's exclusion principle inevitable. Vectors, I remember Paul Halmos in his book on algebra, linear algebra, mentioned that vectors are things that can be multiplied by numbers and added together to form other vectors in the same vector space. That's a particularly nice idea, a very general definition, and it applies to the inventory of a hardware store. So that's basically what vectors are. They're things that you can multiply by numbers. So U and V are vectors if you can multiply them by numbers and get another vector. A basis for a vector space is a set of vectors such that every vector in the vector space can be written as a linear combination of the vectors with numbers. And one of the tricky things here is, well, we say numbers. Do we mean real numbers, complex numbers, or what? And according to that, you can, for a given set of vectors, you get a given set of basis vectors, you get a different vector space according to whether you're allowed to use complex numbers or not. But, you know, and context usually makes it obvious what we're doing. So I'm going to skip all these examples here. As I said, it's useful for you to review them, especially if you haven't had a lot of training in linear algebra. By the way, the nice thing about linear algebra is that if you can take a physics problem and express it as a problem in linear algebra, you can then use a computer to solve it numerically. Another thing is that when computers do mathematics, for practical purposes, what they're doing is linear algebra, because they don't do integrals in some fancy way. Typically, they do integrals by doing an actual sum, and that's linear algebra. Of course, MATLAB and Mathematica and some other Maple, some other programs, Maxima, these programs can do symbolic integration for you, and that's quite wonderful when it can be done. Cross products, I'm sure you learned about these in high school, if not in graduate school and undergraduate school. So I'm just going to mention that one way of thinking about them, in fact, this is the way I think about them, is that if you have three vectors, x and y, the ith component is a sum of xj, yk, sum j and k going from 1 to 3, with this little epsilon ijk there. And this is a nice way to think about it, because it gives you an exact formula which has very nice properties, because this eijk, which is sometimes called the Levi-Civitas symbol, it's something that's totally anti-symmetric. And so epsilon 1, 2, 3 is 1, and that basically is all you need to know, that epsilon 1, 2, 3 is 1. So since it's totally anti-symmetric, if you move the 1 across the 2 and across the 3, you get 2 minus signs, so it doesn't change. On the other hand, if you just interchange 2 with 1, you get a minus sign, and then you get these, and these are the only 6 that are non-zero. And then all these ones where one index is repeated, 1 or 2 indices are repeated, gives you just 0. And an example of that, of course, is angular momentum. That's angular momentum about a point is Ri across Pi, Ri minus Q, where Q is the origin. I'm going to skip rotations and rotating coordinate system. I don't think this is something that might go into a third edition of the book. As I said, I'll put this on the class webpage, and you can look at it, but I don't think it's important enough to stress today. Linear operators, well, the linear operator A is just something that maps a vector, maps every vector in its domain into a vector in its range in a way that's linear. And what that means is that A on B, B a number, C a number, V a vector, W a vector, in its domain, it maps that sum into B times A of V plus C times A of W, or we'd normally write it as just BAV plus CAW. And typically the domain and the range are the same vector space. And then A maps a given basis for the for S into a linear combination of the basis vectors. We're going to get to Dirac's notation in a minute, which makes things, I think, a lot clearer. The square matrix represents the linear operator in a particular basis. And so A on a vector U, which looks like this, is AKI on BK. Well, it's actually right. AKI on, well, it's A on BI is AKI BK. And you might think that's crazy that this I've got the K in the wrong place, but it actually works out. So the kth component of the vector U prime K is AKI, AK1, U1, so on and so forth on the actual elements. So it looks like this. You see the coefficient of BK is AK1. The kth component of U prime is this structure, which is this sum. Anyway, I think it's clearer if you read it than if I try to recite it to you. Linear operators are unique, but the matrix that represents a given a given operator depends upon the basis. So in other words, you have a linear operator and you then represent the linear operator as a matrix by using a basis. And depending on which basis you choose, you get a different matrix. And so that's illustrated here in some more detail. And in particular, the matrix that represents A in the B prime basis is related, is related to the matrix A that represents it in the B matrix basis by a similarity transformation. And the similarity transformation is just U inverse AU. Although here, this U is typically unitary. Well, not always unitary. In fact, any transformation of the form U inverse AU is a similarity transformation. If U is unitary, then U inverse is actually U dagger, the Hermitian adjoint, and then A prime is U dagger AU. So these are rules that are used all the time in quantum mechanics, and so you should make sure that you understand them and come to terms with them. Because traces are cyclic, they're invariant under similarity transformations, and that's one of the things that we like about traces, namely that they're invariant under similarity transformations, and in particular then if A represents some kind of physical operator or physical quantity, the trace of that operator will be independent of the basis that you're using. And that, of course, is what we want. We don't want our physical quantities to be dependent upon what crazy basis we happen to choose. Inner products. Inner products are, of course, quite important. I'm just looking over here to see how far. Yes, okay. Inner products are used all the time by physicists. A positive definite inner product is sort of the gold standard inner product. It's the one we like best, and it's the one that's used essentially universally all the time in quantum mechanics. But there are others that are useful in more general contexts. So a positive definite inner product associates a number with every ordered pair of vectors Fg in the vector space and obeys for every 3 vectors in the vector space and any 2 numbers where V here, why am I talking about V? Oh, V is this V. V is ZG plus WH. So this is just a multiples of these 2 vectors. it obeys these rules. And the first is that, well, this is just the statement that this inner product is an inner product in the sense that I defined it earlier in this lecture today, so that F comma G is G comma F complex conjugate. Moreover, the inner product is linear in the first element. So F on Z, remember Z and W are complex. F on ZG plus WH, G and H being vectors, is Z, complex number Z times the inner product of F with G plus the complex number W times the inner product of F with H. And the inner product of a vector with itself is always non-negative, and it can only be zero if the vector itself is zero. So that's the kind of inner product that we really like, because when we use it, if that's the inner product that we have, then it's more useful than other inner products. The first says that the inner product is Hermitian. The second says it's linear in the second vector. The third says that it's positive definite, and the first two rules imply that the inner product is antilinear in the first pair. So ZG plus WH, inner product with F, is Z star GF plus W star HF. Now there's a more general inner product called the Schwarz inner product, and it obeys the first two rules, but not, so the first two rules, it obeys these two rules, but not this third rule. It's got a weakened third rule. Namely, it's just that the inner product, the Schwarz inner product of a vector with self has to be non-negative, but the third rule doesn't hold. Only the first part of the third rule. And the fourth rule, of course, the consequence of the first two, so it's automatic. So if you've gotten confused here, the fourth rule is simply this. The condition of non-negativity implies that a vector of zero length must be orthogonal to all the vectors in the vector space, but F need not be identically zero. So it's kind of a subtle special case. Now, these inner products that we're most used to, or that we use most of the time, are positive or positive definite, or non-negative. On the other hand, you can have inner products that are indefinite, and then the inner product obeys the first two rules and the fourth rule, but instead you'd want your inner product to be non-degenerate. So if FG is zero for all F in the vector space, then G is zero. So that says that only the zero vector is orthogonal to all vectors of the space. And the positive definite condition is stronger than this condition. Stronger than the non-degeneracy condition. Let me just write a note to myself. So for inner products that are positive or positive definite, we can define a norm or a length, and that's just the square root of the inner product of the vector with itself. So this is said to be the norm. There are fancier norms that have been defined, and it's certainly possible to define such things. I'm going to skip again these examples. but maybe pause here to say a vector space with a positive definite inner product is called an inner product space, a metric space, or a pre-Hilbert space. And these are terms that are sort of worth worth emphasizing. So let me just do that. There's another concept here that actually is used later in the book, so I'll mention it here. A sequence of vectors forms a Cauchy sequence or a Cauchy sequence if for every epsilon greater than 0, there's some large integer that depends upon epsilon such that the norm of the difference of the two vectors is less than epsilon whenever n and m both exceed capital N. So basically, it's saying that these, in a Cauchy sequence, these vectors get closer and closer together as you go farther and farther out, but in this precise mathematical way. The sequence of vectors converges to a vector if for every epsilon is an integer n such that this difference is less than epsilon wherever n exceeds n of epsilon. So I think that's something you know about. An inner product space with a norm defined as earlier. So let me just see if I can flash that definition. Well, all right. So the norm was the square root of the inner product. An inner product space with a norm is complete. So complete here is a technical term that I'm going to put in maroon or whatever that color is, magenta. So it's complete if each of its Cauchy sequences converges to a vector in the space. A Hilbert space is a complete inner product space. So that's another thing that one wants to emphasize. We always talk about Hilbert spaces in quantum mechanics. And they're, on the other hand, rarely defined in physics courses. An example, just to connect with quantum mechanics, an example is a Hilbert space of square integrable functions. So you can take the inner product of two complex functions as an integral from a to b of f star g. And the squared norm is then the integral from a to b of that. And this function square integral, of course, if its norm is finite, and the space of all square integrable functions is an inner product space. It's also complete and is a Hilbert space. And so this is the Hilbert space that we use in quantum mechanics. I don't know why the hell we call it a Hilbert space, but I guess some friend of Hilbert's calls it a Hilbert space. A Minkowski product is an inner product that is indefinite. Let me note that, sorry about that. Why is that? It keeps coming back. I'm trying to make this bigger and I'm not able to. There, okay. Okay, so that's the Hilbert space of the square integrable functions. The Minkowski or Lorentz inner product is just the dot product of the three vectors minus the product of the fourth components. So that's the inner product of a vector, of a full vector with itself. There are, however, two conventions for this, and unfortunately, they're both very common. In fact, the one I'm using has 3 plus signs, 1 minus sign. Many people in particle physics use 3 minus signs and 1 plus sign. And They do that because if the vector represents not a 4-vector of position space or a general 4-vector, but rather the 4-vector of the 4 momentum of a physical particle, then the square of the 0th component is greater than the sum than the other sums. And so they want p squared to be m squared, whereas here p squared is minus m squared times c squared. Physicists often set c equal to 1 and h bar equal to 1. I've tried not to do that, but that has been at great cost to me, and I may have slipped up here or there. So let me urge you to read these examples. We, in fact, in a certain sense, learn more from examples than we do from general principles. And maybe I should teach this course by just doing the examples and letting the students invent the general theorems from the examples. But I've never tried to do that. Anyway, there's something called the Schwarz inequality, and it's the inner product of f with f times the inner product of g with g is greater than or equal to the inner product of f with g, absolute value squared. And that's called the Schwarz inequality. It holds for any Schwarz in a product. And therefore, it also holds for any positive definite inner product, which has more properties. It gives you the triangle inequality. The norm of f plus g is less than or equal to norm of f plus norm of g. Okay, linear independence and completeness. The way mathematicians define linear independence and completeness is, I always find it to be amusing, because you say, well, what they say is a set of n vectors is linearly dependent over the real or complex numbers if there exist real or complex numbers, not all 0, such that the linear combination vanishes. And then the thing we actually need is the definition of a set of vectors that are linearly independent, and that's that they're linearly independent if they're not linearly dependent. So I don't know, that always kind of makes me chuckle. A set of linearly independent vectors is maximal in a vector space if the addition of any other vector to the set makes the enlarged set linearly dependent. A set of n linearly independent vectors that is maximal in a vector space can represent any vector u in the vector space as a linear combination of these vectors. And the reason is that if you enlarge the set by adding u to it, you get something that can be written as a sum of the u plus all the v's times c's that are not all 0 is equal to 0, and C0 can't be 0 because the v's will be linearly dependent, and so you write u as minus 1 over c times these, and so you've been able to, you see then that a maximal set of linearly independent vectors is complete. The maximum number of linearly independent vectors in a space is called the dimension of the space. That's the dimension of a vector space. And if you have any two bases, or bases, I really don't know what the plural is of bases, what the plural of base is, and it's quite confusing. One of you may know, so shout it out. Anyway, if you have any two bases or bases in a vector space, then they have to have the same dimension. So I'm going to skip the proof. This number is called, of course, the dimension of the space. Orthonormal vectors. Well, if we have some linearly independent vectors, then we can make out of them a set of n vectors that are linear, that are orthonormal. Orthonormal means the inner product is the Kronecker delta. So it's 1 if I equals j and 0 otherwise. So they're all mutually orthogonal. There are many ways of to do this. The famous one is the Graham-Schmidt method. And basically, you just take the first vector and normalize it, and that's your first vector. The next one is you take the second vector minus a certain linear combination, a certain complex number times the first vector, and you get U2. Then you normalize U2, and then you show that U2, in fact, is orthogonal. In fact, the way I chose this number here was by insisting that U2 be orthogonal to U1. And you go on in that way, and you get the kth vector is the kth vector of the new set minus, and you have to do the sum to make sure that VK doesn't, that UK isn't going to have any overlap with any of the previous orthonormal vectors. And it turns out that Dirac's notation is a nice way of expressing this Graham-Schmidt procedure. Let me just mention that if you do the Graham-Schmidt procedure in a different order, that is to say, instead of taking the vectors V1, V2 up to Vn, you start with, say, V3, and then you go to V4, and then you bring in V1, you get a different set of orthonormal vectors. You don't get the same set, you get a different set, which is kind of amusing. And that's just another illustration of the fact that there are many, many bases or orthonormal bases for any vector space. Outer products. Now, this outer product, as I mentioned earlier, is something that isn't taught that much, especially to physics graduate students or physics undergraduates, in fact, for that matter, physics graduate students. And but it's something that is quite important, and it's something that Dirac introduced a notation for. And in fact, the advantage of Dirac notation is that it's a notation that makes it possible to write outer products in a precise way. So for any two vectors, we can make an F and G, we can make an outer product that maps a vector H into the vector F multiplied by this inner product. So A on H is F times GH. And you see in this notation, it's kind of confusing. We're starting with F and G, and A maps H into a multiple of F, and the multiple is the inner product of G with H. And you can see that it's linear, and you can write it in component form this way. And so in this particular basis where the components are of the vectors are Fi, Gi, and Hi, the outer product is Fi, G, J star. That's Aij. We'll get to Dirac's notation is coming up shortly, and that is one of the advantages of Dirac notation, that it makes this plain. And we say A is the outer product of the vector F with the row vector G. That's what this is. Okay, so I will do these examples. Suppose F is this vector, G is that vector. The outer products of F with G is this, and the outer product of G with F is that. And now, Dirac's notation is just marvelous for this, namely that if you have a vector F, well, he writes it as a ket, and a vector G, he writes also as a ket G. And so the previous example more generally would look this way. F might be ABC, G might be ZW. Then the bra corresponding to F is A star, B star, C star, and the bra corresponding to G is Z star, W star. And the outer products, there are two outer products, F with G, and so you just take the F like this and multiply it by G star, and you just sort of multiply willy-nilly, and you get 3 times 2, which you get 6 elements. And if you do it the other way, if you do Z times F, in other words, the ket G and the bra F, then you also get 6, but they're a different set of 6. In fact, they're the complex conjugate and transpose, the adjoint is what you get. F with F gives you this, and G with G gives you that. So he called a vector F a ket, and the new thing that he invented was the bra, and this is what makes outer products, makes it easy to write outer products. And so the inner product of two vectors is he called the bracket, and that's why he called them the bra and the ket. And in fact, if you have the matrix element of an operator C, you'd write it as GCF, and in ordinary notation, it would be GCF, but in Dirac's notation, it's bra G, C, ket F, and so that's bracket of the operator C. In fact, I ought to make this, I think, well, all right, I guess it's okay to have it like that. Anyway, so in Dirac notation, an outer product like 140 AH, in other words, GHF equal to FGH, you just write it this way, A on H. The outer A is written as the outer product with F with H, F with G. And you just take this thing here and multiply by H, and the overlapping vertical lines, you just coalesce into one line. This is then an inner product, and you see exactly that his notation makes it work exactly as it should. The bra G is the adjoint or Hermitian adjoint or conjugate transpose or Hermitian transpose of the ket G, and the ket F is the adjoint of the bra F. So you can write things this way: bra is ket adjoint, ket is adjoint of bra, the double adjoint of the bra is the bra, and the double adjoint of the ket is the ket. And the adjoint of an outer product looks like that. And the most general linear operator in Dirac's notation is an arbitrary combination of outer products of vector k with vector l and coefficient zkl. The adjoint is this, and you just flip the l to l, bra l becomes ket l, ket k becomes bra k, zkl becomes z star kl. And so this is, all these manipulations in quantum mechanics are transparent when you write them in Dirac notation, or at least they're clearer than if you write them in ordinary notation, where they can be mysterious. And the adjoint of the ket H, which is AF, is the adjoint of this, and so you get Z star KL. LK is adjoint, or complex conjugate is FL, and ket K goes into bra K, and that's FA adjoint. And so before Dirac, bras were implicit, but did not declare explicitly, and there was no simple way of writing outer products, whereas they're extremely important in quantum mechanics. If the kets form an orthonormal basis, we can expand an arbitrary ket in the space like that. Since the basis vectors are orthogonal, we can, or orthonormal, I should say. Orthonormal means that they're not only orthogonal, but they're also normalized. We can identify the coefficients just by taking this inner product like that, and we get this the L coefficient of the vector of the ket F. And one way of writing a vector is as the vector as a ket being operated on by the sum of the outer products of all the orthonormal basis vectors kk. And so that tells us then that the identity operator is just this sum. And for every set of vectors that forms an orthonormal basis in a vector space, you get an equivalent representation of the identity operator. These are sometimes called resolutions of the identity operator. And so I guess I can let you read these things. Here's the Gram-Schmidt and Dirac's procedure in Dirac's notation. You can see it's much simpler. You just write UK as 1 minus the sum of the orthogonal of the outer products of the U's with VK. And where, all right, anyway, I'm going to just go on. Vectors and linear operators are abstract and unique, but the numbers that we compute with are inner products, and these vary according to our choice of basis. So you can compute this inner product if you know the components of F and G in some basis. And here the inner product of G with F is this, and it's invariant. You get the same inner product no matter which set of orthonormal basis vectors you use, the K's or the alpha K's. And the same thing with what I could have written as a bracket. It then is, it doesn't matter whether you use the K or orthonormal vectors or the L's or the, I'm sorry, the K, L's or the alphas. And if you take a sum of outer products of the basis vectors of two different bases, what you get is a unitary operator that moves you from one basis to another. The adjoint, well, as we said, the most general operator, well, first of all, the adjoint of the basic linear operator Z times the outer product of ket K with bra L is just Z star LK. And so if you write the most general linear operator this way, its adjoint then looks like this. You basically get automatically the complex conjugate times the transpose. And you find the adjoint of the adjoint is the original matrix. Okay, so self-adjoint or Hermitian operators, well, these are operators that whose adjoint is the operator itself. And so it's basically that AKL is A LK star. So I should have written ALK star there, I think, 1.183. Anyway, other ways of thinking about this in Dirac notation are like that. So let's just look at this a little bit. You see, here we have the linear operator, the abstract linear operator on the abstract vector. And in Dirac's notation, that can be written as A on the ket F. And here, G, we can, if this is a Hermitian operator, then we can move the A in front of the G. And then, of course, that's the same thing as FAG complex conjugate, which is then FAG complex conjugate. And that's also the same thing as AFG star. Anyway, this is only true for Hermitian operators. If A were not Hermitian, then this would be that, but we'd need a dagger here. And then we'd have a dagger there. And then we'd have a dagger there. And I don't think we need a dagger there. No, so if we have a dagger here, we don't have a dagger there. If I've got this straight, I have to think of it more carefully. Anyway, a matrix that is real and symmetric is Hermitian. A matrix that's imaginary and anti-symmetric is Hermitian. Anti-symmetric, of course, just so a matrix A, IJ equals A, JI, this is a J, that's symmetric. A, IJ equals minus a J, I, anti-symmetric. Okay, so notice that if you have a self-adjoint linear operator, it can be represented in a given basis by a matrix that's real and symmetric or imaginary and antisymmetric. But if you change bases, it doesn't stay real and symmetric typically, or imaginary and antisymmetric. So a Hermitian matrix can be more confusing than real and symmetric or imaginary and antisymmetric if it's represented in an arbitrary basis. An eigenvector of a linear operator with eigenvalue A is if this equation is true. So this is basically the eigenvector and eigenvalue. This use of German, of course, is because the Germans basically invented quantum mechanics, or at least they actually, I don't know, there were whole sorts of people who started. Well, it was Einstein and then Heisenberg and Schrodinger, but on the other hand, the Danish Bohr, the Dane Bohr got in there with the first sensible model of the hydrogen atom. And then, of course, the person who put it in really great shape and moved it forward was Dirac. Fiat's identities, if you're a theorist, you want to understand them, so read this example, but I don't think we have to go through it in detail now. Real symmetric operators, well, are such that a real linear operator on a real vector space is represented by a real matrix. So, of course, in ordinary classical mechanics and much of classical physics, one doesn't use complex numbers. One can get away with not using them. On the other hand, if you have if a matrix is real and symmetric, then it's automatically Hermitian. Unitary operators are operators whose adjoint is the inverse. So U adjoint is U adjoint U is the identity. And an operator that changes from one orthonormal basis to another is automatically unitary. Here's the proof. And you can say that an operator is unitary if and only if it maps every orthonormal basis into an orthonormal basis. And so we represent changes of basis by unitary operators. And curiously, one can think in physics, especially in quantum mechanics, of a basis as being a coordinate system of vectors, for example. And if you change from one coordinate system to another by a rotation, well, you want to represent that by a unitary matrix. And if you change by translating the experiment, moving it from one place in the lab to another, that also should be represented. That's a change of basis, and it's represented by a unitary transformation. Dirac's delta function, one of the million things he introduced, is, first of all, it's not strictly speaking a function, it's what's called a functional. And the sense in which it's a functional is the following. The Dirac delta function associated with the point x prime maps the function f into its value at x prime. And in physics, we often write it as delta of x minus x prime, f of x dx. The reason why it's useful to do that is that Fourier transforms often turn into delta functions. And even though we keep saying that it's a functional, not a function, we keep referring to it as a delta function. And, you know, well, language is loose. Okay. Here are some examples of change of basis as translations and rotations. There's also something that is worth knowing about, but we're not going to be using it much, or if at all, anti-unitary, anti-linear operators. So if it's anti-linear, K on Z psi plus W phi is this, and anti-unitary means that K phi inner product with K psi is psi phi. So it's quite different, and you might say, where is it used? As far as I know, the only time I've seen that I can remember seeing an anti-unitary or anti-linear operator is in discussions of time reversal. And time reversal, of course, is pretty spooky. Of course, if we had time reversal, we could fix many mistakes of the past. And I'd love to have a little bit of time reversal. It'd be so handy. Symmetry in quantum mechanics. Well, a symmetry is well, actually, we're down to the last minute. So I'm going to stop here at symmetry. And in fact, I think I'll write this title in color if I can, and that will be where we'll start tomorrow. And somehow I screwed up. Hold on.
Are we going to cover what homework assignments and the like will look like over the semester?
Oh, good point. Good point. Basically, I'll be assigning a lot of homework because homework is a way of learning. And so the homework problems will basically be the problems that are already in the book. I may invent some new ones. I will I will send you all an email with the homework problems, and I may list them also on the class webpage. The class webpage is listed on the departmental webpage under classes and class web pages. So I may assign the homework tomorrow, but I'm not going to. I haven't picked out the problems yet today.
Do you know how you would like homeworks turned in or submitted to you?
Well, not to me. They're going to be submitted to the grader, and I'll give you the grader's email. I think you should all learn TeX and LaTeX and do your homework in LaTeX, but that's not necessary. And so what you could do is just write your homework on paper and put your homework solutions in the box, the mailbox of the grader in Pais somewhere on the first floor, the ground floor of Pais. Or you can write the homework on paper and pencil and paper, and then scan it and send the grader a scan of your homework. So do it any way you want. LaTeX is actually very easy to use once you get started. And the easiest way to get started is to grab an example and just change the example. And whenever you don't need something, you can use the web, Google, or there's a commercial product on the web that is sort of a laboratory for doing LaTeX, and it might be easier. I don't use it, frankly, or hardly ever. If I don't know something, I Google it and usually find out from Googling it. So anyway, what I would suggest, though, is that you, as I give you homework after a week or two, send me an email, talk with your friends and send me an email saying, we need more homework or we need less homework. So, I don't want to assign too much homework. I once was teaching quantum mechanics years ago, and I had a marvelous grader who just never complained, worked like hell, was very smart. And in those days, the TA would do the homework problems. And I was teaching out of a very good book, which has 3 authors, a book on quantum mechanics, one of them a Nobel laureate. They're all French, but I forget the name of the book. It's a huge 2-volume. Volume 1 is that thick and volume 2 is this thick. And there are chapters which are essential and complements, which are kind of like examples. And it's an excellent book. And I just assigned all the problems, and the students didn't complain, and the grader didn't complain. And only much later did I realize that I was absolutely abusing the students by giving them much too much homework. So I urge you to complain and make suggestions because people make mistakes, and I'm one of that huge group called people. So I make mistakes. And also, if there's something you'd particularly like to learn about, send me an email or speak up about it. What else? Oh, you know what? I made a mistake as to when the class ended. I somehow thought that it ended at 6:10. Of course, it ends at 6:15. But I guess it was useful to spend the class time talking about homework problems. So I will try to get these posted or sent to you on an email. And if you have a friend who registers for the course late, ask him or her to send me his or her email so that I add that email to the class list for Zoom and homework assignments.
Would you still like us to use the second edition of the book, or?
Oh, God, yes.
Okay, yeah, because you mentioned you're working on this third edition.
Yeah, well,
And some of
the third edition doesn't exist and may never
Gotcha.
exist. It probably will never exist except at UNM. And the second edition has things that the first edition doesn't have, and I think you can buy the second edition used. So if money is an issue. By the way, the books by Cambridge University Press are no more than 2/3 the cost of the books published by American publishers. So the cost of this book is minor compared to the books put out by published by Elsevier, against whom I declared war about 15 years ago. Anyway, all right. Well, I'm happy to hang around for a few minutes to see about extra questions. No one's asked a question yet, and if you'd like to, if there's something that, I mean, did I go too fast or too slow, or is there something you'd like me to repeat or be sure to cover tomorrow? So as I said in some of my emails, 468 should be regarded as part of 466. And you should register for 468 if you have enough credit hours. If you don't have enough credit hours, just attend 468. And because if we're going to try to cover more than the first 10 chapters, we need to use the Wednesday class as a real class. And then we can get through the stuff that you all sort of were taught as undergraduates or high school students, and get on to things that are more interesting, like general relativity, which has become more important because of advances in astronomy and physics. There are now atomic clocks where you can see the time change, the rate of change of time as you move the clock a foot or so up or down. And of course, there are also gravitational waves due to the merging of black holes billions of kilometers away. And we have dark matter and dark energy, and we don't know what it is, or what they are, I should say. And so there are all sorts, and both dark energy and dark matter came in through an understanding of gravity, because dark matter and dark energy so far have been observed only gravitationally. So general relativity is more important than it used to be. All right, well, I'm gonna, I guess, stop now unless there's another question. And I hope I recorded this session, and if I have recorded it, I will post it in a suitable place and tell you where it is. So let me see what we've got here. I'm not sure I've been recording. So let me see. Stop recording. Let's see if anything. All right, so I'm going to stop now. Have a nice evening, everybody. And class tomorrow is at 5:30, and it's only 50 minutes on Wednesdays. So stop recording.